Welcome to Zoom. Enter your meeting ID followed by pound. You have not entered any numbers. Please re-enter your meeting ID followed by pound. You have not entered any numbers. Please re-enter your meeting ID followed by pound. Goodbye. Welcome to Zoom. You have not entered any numbers. Please. You are the meeting host. Please enter your host key followed by pound. If you are a participant, please press pound to continue. The meeting has not started. Please wait for 5 minutes.
Okay, thank you. Actually, I wasn't quite as dumb as everybody I saw on the news last night. They kept doing the mute thing. Mine was evidently I just never hit the join audio part. So I'm a crackhead. I apologize. Anyway, so what I was saying, on this video as well as the one we made on Monday, your names are actually appearing, your usernames are appearing up here. So if you guys, because I'm posting all these videos to YouTube and then reposting them back on our page, that means your names are actually showing on YouTube. If you don't want that shown, then change these names before next meeting, or ideally during this meeting if you can. And also, if you have a problem with those last two, let me know. I'll go back in and see if I can't edit out your names. But for the future, all of these will be posted on YouTube. So if you don't want your name to show, then you definitely need to change that to something like just your initials or something like that. Okay. Maybe the first 3 letters of your first name and the first 3 letters of your last name. That way I can easily tell the role, but you also, people looking at the video would be hard pressed to tell who y'all are. So like I said, if you have a problem with that, I apologize. I should have let you know that beforehand. I'm building up a number of hours in my YouTube channel. I'll actually send y'all a link to my YouTube channel directly, so you don't have to go through the intermediate process of going to Canvas and then all that stuff. Plus, like, I often make videos not during lab. Like this morning I made 3 of them, only 1 survived. So I got 3 hours of content made, but only about 20 minutes existed worthwhile. So it's now going up on YouTube as we speak. But if you're actually if you've actually joined my YouTube channel, then you can get notifications every time I post anything. And I'll be posting stuff there for your class as well as for astronomy classes. Next semester it'll be the calculus-based physics class, all that good stuff. So it's just a page that I'm slowly developing. I'm going to try to make it sort of it to be a repository for anybody that needs any help with any physics course, all the way up through senior level physics courses, mathematics courses as well. And astronomy courses. So does anybody have any questions about last time, or course questions, or anything whatsoever? Okay, that's a pretty good sign then. All right, got people changing their stuff already. So, and feel free to, chat with me privately or publicly, it doesn't matter, over on the right. I'll try to pay attention to that as much as I can. When we last spoke, we had started into Coulomb's law, where the force is proportional to the product of the charges and inversely proportional to the square of the distance between them. And then the direction is always along the line connecting the centers of the 2 charges. Now, what does center mean? Well, that luckily something you don't have to worry about in the algebra-based physics. But basically what it means is, in some sense, there's a center of charge, but what you're going to do is assume that the distances between the individual objects is larger, say by a factor of 10, than the actual dimensions of the charged object, in which case you can just say the center is close enough, okay? That's our rule of thumb. If you want to compare something and you think something is much bigger than something else, in other words, you can ignore that smaller thing, then it has to be at least a factor of 10 smaller. So factor of 10 is good, a factor of 100 is even better, a factor of 1,000 is really good, but bare minimum has got to be a factor of 10 smaller if you want to ignore any particular distance or any particular size. So last time, like I said, we did do Coulomb's law. I talked about how to induce a charge, how to conduct charge. In other words, how do you charge something by conduction and induction. I've posted the video. It's on the module for week 1. I also posted 2 videos by Shini Sumara. That's the Crash Course Physics instructor put out by PBS on YouTube. She's really awesome. It's a good intro, but it's also calculus-based physics, so sometimes you'll run into integrals and derivatives, but she still gives you another option to look at. You can also find all sorts of help on probably Khan Academy and various other videos, but really I'm trying to make this course, these videos for this course, good enough where you can go without anything else. But if you get confused, it's always good to find another resource. Like I mentioned, the Sean's outlines, as you see right there, that red and yellow book. Also, any other videos you might find are good. MIT has all their courses on there, but the lowest level of physics MIT has is the calculus base. Same thing with Stanford and a lot of these schools. So it's kind of hard to find those, but there's really good instructors like Walter Lewin, Lewin. If you want to do a Google search for him on YouTube, you'll find all sorts of cool physics demos that he does. In general, MIT has a great presence on the web. Stanford does too, through iTunes U and stuff like that. So today we're supposed to finish up what we're doing in chapter 16. And before I go with that, I want to let y'all know something about that. So the homeworks I'm making up are pretty much covering all the chapter. So like if I give you a homework assignment for chapter 16, it's going to cover all of chapter 16. And I'm only covering the parts that I plan on testing you on. So for instance, there's a section back here, I think 1610. Yeah, 1610. I don't necessarily cover that, but don't be surprised if you see that topic or 1611 or 1612 topics in your homeworks. But you do not have to worry about those appearing in your actual test. Okay, they'll appear in the practice test, they'll appear in the homework, but they're not necessarily going to appear they're definitely not going to appear in the test. So only the sections that I cover are going to appear on the tests. I want to make sure y'all knew that. So last time we went up through more or less, we got up to the part where you start in the electric field, which would be 16.7, but we had done basically everything up in 16.6. So we're ready to start now with the concept of an electric field. So the problem is if you have, let's say, a charge here, like that, and a charge here, like that. Just imagine the end of those pins being point charges. In some way, Coulomb's law suggests that this object can put a force on this object and vice versa without touching them. That's called action at a distance, and it bothered everyone, including Newton when he first introduced his law of gravity, but he didn't know how to solve the problem. He just knew that he could solve a lot of physics problems by assuming it happened and then using the law that he was able to derive for the law of gravity. So the similar thing happened with the Coulomb forces. You basically just say, well, I don't know how it's happening, but it is, right? But they later came along, Michael Faraday did, and introduced the concept of an electric field. So I want to give you an idea of what we mean by the word field. I know you've heard of it on various sci-fi movies and stuff like that, Star Trek, Star Wars, all those good things, where they talk about a force field and all that stuff. Really, what we mean when we say a field is you imagine, let's say, a room. It could actually be all space, and in general, most fields that we deal with are actually defined over all the universe, basically. But take any region of space, any three-dimensional region, and every point in that, which obviously you can tell there's an infinite number of them, every point of them in that space, you assign to it a value. Let's say the temperature. If you do that, then you then have a temperature field. So that every time I put in an X, Y, and Z coordinate, 3 numbers to find a location in a room, out pops a temperature, 32 Celsius or something, which is god awful hot, right? But that is the concept of a field. You just apply some value to every point in space, and then you have a field. Now, those fields can be scalar field, like the temperature field I just mentioned, or they can be a vector field, in which case you have to have a magnitude and direction. Yeah, I don't know if you recall from Despicable Me 1, the bad guy's name was, anybody recall? Who's the bad guy in Despicable Me 1? His name was Vector. And he called himself Vector because he does evil with direction and magnitude. And so it's actually a correct definition of a vector. A vector is something that has magnitude and direction. So a vector field is literally you assigning every point in space a magnitude and a direction. One example of that would be a force field, because forces are vectors. A torque field, that's sort of a vector. There's some weird stuff going on with that. But anyways, the electric field, which is what we're talking about now, is another example. So what we're going to do is try to think of a field. So instead of thinking of this particle and this particle touching each other, or not touching each other, but applying a force to each other without touching, now we can say, hey, this guy right here is the source of something we're going to call an electric field, and this guy just feels it. So what we're going to do is we're going to imagine this blue charged particle creating some distortion of the space around it, like this, okay? And then we measure that distortion, and if we need the force out, we just multiply that distortion by the charge of this red guy, and that gives us the electric field, or that gives us the force. So in some sense, we got to think of Coulomb's law, because we need to be able to get the force out of it, right? We still need K, Q1, Q2 over distance squared to get the force out. We know how to calculate that with Coulomb's law, but we want to get rid of the actual idea that this one, or excuse me, that this one was doing anything. So this blue one's the source, this red one's the thing experiencing it. So if you took Coulomb's law and literally just divided out the charge of the red one, then you'd have something that's units of force, because the Coulomb's law came out in newtons, but it doesn't have the Coulomb, the extra Coulomb that you needed to actually make it a newton, so it's a newton per Coulomb. That would be the electric field. So let me share my screen a second. No, I don't want to share screen. I want to change to my document cam. So let me change to my document cam a second. So what we're going to do, here's my wording for the field: an assignment of some value to every point in space or some part of space. For example, temperature field, gravitational field, electric field. So the electric field you can think of as Coulomb's law divided by the charge that was actually experiencing the force, right? So you think of one as the source of the electric field and the other one as the charge experiencing the electric field, and you divide out the one experiencing it and you leave in the charge causing it. Now in principle, that's a little problematic, because if I have an electric field and I go putting a charge in it, then that electric field creates another electric field, or is disturbed by this new charge that creates another electric field. So what we do is we sort of formally think about trying smaller and smaller and smaller charges Q until we get so close to zero that it really doesn't matter. And when you do that, you can slowly get out what the actual electric field is, because there is some chance, long as Q is finite, that it's going to actually disturb the existing electric field just by its presence. So that's really formally what we do. And in practice, you don't have to do a thing. Okay, so it doesn't make the problems any more difficult or anything like that. You're just consistently going to take the Coulomb force that you found and divide it by Q, and that'll give you the actual electric field equation. So what does that mean? Well, we had the Coulomb force is equal to K Q over R squared, right? Where this one's the Q that I consider the source, and this is the Q that I consider to be the one affected by it. So the electric field is just F over the one being affected. So the magnitude of it becomes K Q over R squared. So that's the new electric field equation that we'll use. Notice it's also called Coulomb's law, by the way, but notice it looks just like Coulomb's law, only it has one charge instead of two. And the units turn out to be units of newtons per coulomb. Later, we'll find another unit that it's equivalent to, namely the volt per meter, but it basically is just a newton per coulomb because it's the number of newtons experienced for every coulomb that you put in it. So at the end of all this, this tells us two things. One, we can get the force by multiplying the charge by the electric field. And technically, electric field's a vector, so is the force, which we already knew. So this is actually a vector equation as well. So that's what the electric field is, and it just gives us, like I said, a way of sort of circumventing the problem of action at a distance. But in the end, once we pretended this field existed, we made predictions based on it existing. And thank you, somebody did know the answer that it was vector. Awesome. But we did actually find that this imaginary thing, this thing that Michael Faraday imagined, the electric field, existed. And we made predictions based on what we would see if it did exist, and lo and behold, those experiments came true. So in some sense, we ultimately learned that there is something considered to be an electric field. So the electric field is a powerful thing, not only conceptually to get us out of the action at a distance, but it turns out to be a very real thing that we can measure. And you'll see in lab today that you can actually measure it. That's what our lab is going to be today, is determining the electric field. We used to do it with real physical objects, but obviously with the quarantine, we can't have everybody in a small classroom, so we're doing it with a simulation software. So what is the direction of the electric field? We know now how to calculate the magnitude. Remember, before, the force was the product of the charges and inversely related to the square of the distance between them. See some chat going on. So the paper's really blurry for everyone. Yeah, my bandwidth is kind of crappy right now. Let me, hold on a second. Let me see if I can do something. Oh, okay. So I've got 3 minutes left. There's that video that I made this morning, that last one is uploading. So that's why the actual image is kind of crappy right now. So don't worry too much. It'll clear up really soon. I want to make sure y'all can see that now. So I'm zooming it in a little better just to make sure everybody sees what's going on there. Okay, and we haven't even got to those drawings yet. So look at them now, and I want to make something clear to you. So we were talking about the electric field. Obviously, the magnitude we can get from that equation right there, E equals KQ over R squared. But with Coulomb's law, we had a very distinct way of finding out the direction. The direction always pointed along the line from the center of Q1 to the center of Q2. So where's the electric field point now? And again, we have to make a decision of what our formal thing is going to be. And we've decided, physicists in general have decided, that electric field lines always point in the direction that a positive charge would be compelled to accelerate if put in that location. Okay, so what do I mean by that? So for instance, if you had a charge Q, like this guy right here, if I put a test charge little q, which is the one we're dividing out, by the way, if I put a test charge little q, say right here, then it would be compelled to run away from the charge Q, big Q, and therefore the direction of the electric field at this point is to the right. Does that make sense to everyone? So the electric field always points in the direction that a positive charge would move if it was free to do so. The length of the line, the length of the electric field lines, is indicative of the strength, but also the number of lines per unit area is indicative of the strength. So for instance, we know that a charge Q would cause an electric field. I'm representing its strength by 4 lines in this circular area. However, if I wanted to double the electric field strength, I could just double the charge Q that's causing the electric field. So that's what I did here. I changed it to 2Q. Well, in order to show that, I either need to make these lines longer, which I chose not to do, or I need to make them more densely packed by a factor of 2. Since I'm only dealing with 2 dimensions, I have to show it in 2 dimensions. So instead of 4 lines, I made 8. Now, in the event of a negative test charge, so let's say we have the same magnitude as this guy, but now it's a negative 2Q test charge, well, then the electric field lines point towards the charge, because if I put a positive charge right here, it would run towards the negative charge. So the electric field lines point towards the center of this charge. But again, since its magnitude is 2Q, I have 8 lines just like I do there. Finally, if I wish to double that still and make it negative 4Q, then instead of 8 lines, I'm going to have 16, and they're all supposed to be the same length. Every line on here is supposed to be the same length because they're all representative of the strength of the electric field, basically halfway out on this arrow, and we're representing it by drawing the arrow there. So all of these should be the same length. All those should be the same length to really be accurate. Now, I didn't try that hard to make them perfect, so obviously they're a little off, but I just wanted to make sure y'all understood that. So that's what the electric field will look like. It actually is continuous though, so you can't just say this is where it is and it stops right there and there's no more electric field. In fact, if I plotted an electric field line at this point, that's maybe twice as far away as this point is. Well, actually, this would be twice as far away. So maybe this is 3 times as far away. So in fact, I'd have to take this length of this arrow and divide it by 9, because 3 squared is 9. And right here, I would put 1/9 as long of an arrow, but it still would point in the exact same direction that's radially outward. Okay, so that's how electric field lines are represented graphically. That'll help you a lot. So let's test what I just claimed. I just claimed, for instance, that if I go 3 times as far out, I would decrease this electric field strength by a factor of 9. Also, if I'd actually put another arrow here, then this is about half as far away as this. So if I put an electric field line here, that's twice as far away as this one that's already represented. So it should be 1/4 the length, because 2 squared is 4. So if this one had a length of 1 inch, say, then right here I'd have to put a 1/4 of an inch, and then right here I'd have to put a 1/9 of an inch. Okay. All right. So let's think about this. Let's say, what is the electric field caused by 1.111? I'm really going to pretend that's 2 sig figs, but I think y'all recognize now that I like to not have to do calculator work. So 0.111 should make you think in a Pavlov's dog sort of way that, oh, that's 1/9. So I'm going to call this 1/9 of a microcoulomb charge. And I'm asking you, what is the electric field caused by 1/9 microcoulomb charge? And I want you to do so by considering its magnitude and direction at distance of 10 centimeters, 20 centimeters, and 30 centimeters. So the electric field, according to Coulomb's law, has a magnitude equal to K Q over R squared. Well, for 10 centimeters, I'll write E sub 10, and that's going to be 9 times 10 to the 9th Newton meters squared per Coulomb squared. Has this cleared up? Are y'all able to see this now pretty well?
Yeah, it's much clearer.
Good. Yeah, the other thing stopped. The thing I was uploading did stop. Okay, so I've got the K. Now I'm going to do 1/9 instead of writing 0.111, 1/9 microcoulomb, so that's 10 times 10 to the negative 6 coulombs over 0.10 meters squared, which really I'm going to think of that as 1/10, and you'll see why in a second. So notice what happens. 9 times 1/9, that's just going to cancel out. So I end up getting 10 to the 9th times 10 to the negative 6th. That gives me 10 to the 3rd. And that's newtons per coulomb, Newton meters squared per coulomb, over 1/10 squared becomes 1/100th. Okay, so you see now what happens is I'm going to have basically 100,000 newtons per coulomb because the meter squared cancels out with the meter squared up there. So that's why I like to use that 0.111 all the time, because it just cancels out with the 9. So now we can see at 10 centimeters, the electric field strength is going to be about 100,000 newtons per coulomb. Now remember, coulomb's a really big unit of charge, so that's why you're getting 100,000 newtons, which is remember, a newton's about a quarter pound, so that's 25,000 pounds, or maybe 12.5 tons. But in order to get that 12.5 tons, you'd have to have a whole coulomb of charge, which is about 1% of a lightning strike. So yeah, that's a buttload of charge. Now let's look at the E for 20. That's equal to 9 times 10 to the 9th Newton meters squared per coulomb squared, again, times 1/9 times 10 to the negative 6 coulombs.
Professor Younger,
Yes, ma'am.
so the 9 times 10 to the 9th, is that a constant?
Yes, that's
Okay.
the constant K that we're going to use. It's actually 8.988, but as you can tell, even if you round it to 2 decimal places, it's still going to be 9.
Okay, so K is always going to be the same for these type of problems, or no?
Yes, it'll always be the same. There is a section later on where you're going to find a way to change K, like if this is not in air or in a vacuum, there's a different K you could use, but you don't have to worry about that for a while.
Okay, thank you.
Okay. All right, so yeah, that's K. We'll also use, by the way, and you'll see it, especially now that we're starting the electric field, K is equivalent to 1/4 pi epsilon naught, so we're going to start using the epsilon naught pretty soon. So it's still 9 times 10 to the 9th, so I recommend you use that often. It makes life easier. So now what we get here is, again, 10 to the 3rd Newton meters squared per coulomb, but now I've got 4 over 100, because when I square 0.2, 0.2 is the same as 2/10. When I square that, that becomes 4/100. So I think you can see that's ultimately going to become 100 times 1,000 times 1,000 would be 100,000, but then I got to divide that by 4, so it's 25,000 newtons per coulomb. So as I suggested earlier, moving I plotted this arrow right here, which I suggested maybe is 1 inch, and that corresponds to the electric field right here at this spot at the tip of my pen. If I go out to here, which is twice as far, then I suggested that one's going to have to be about 1/4 of an inch, because it needs to be about 1/4 as strong. We see here that, in fact, 100 has been divided by 4 and gotten the strength out twice as far to be 1/4 of the strength as it was at 0.1. And then finally, if you want to look at E30, again, I'm going to leave the units off this time. I think we've figured out how all that works out. It's 9 times 10 to the 9th times 1/9 times 10 to the negative 6 over 3/10 meters squared. Again, I think you see what's going to happen. It's 100,000, because this 9 and this 1/9 cancel out. I get 1,000. This 10 squared becomes 100. So that's 100,000. But now I'm going to divide it by 9, because 3 squared is 9. So I get basically dividing 100 by 9 is basically 11.1. So we'd say roughly 11,100 newtons per coulomb. Okay. So to get a feel for what that looks like, this is a positive charge, so I'd put a dot right here to represent our charge Q. And then I'd go out a distance of 0.1 meters, and I'd do a vector like this. Then I go out a distance twice as far, and now the vector needs to be about 1/4 as long, so it's going to be about like that. And then I go out 3 times as far. And it's going to be about 1/9, so maybe like that. And of course, this is repeating itself in every direction because it's spherically symmetric. Okay, so that's actually what the electric field looks like. It's a positive charge, so everywhere along this line it wants to point outward, and everywhere along this circle, which is supposed to be a concentric circle with the center being there, should be exactly this length. And everyone on here should be exactly this length, which is 1/4 of that one. And everyone on this one should be exactly this length, which is supposed to be 1/9 of this one. Does that make sense to everybody? Okay, it looks like everybody's getting it, so that's a good deal. Now that we have this new electric field, we go back to the same thing. Yesterday we talked, or Monday we talked about the the force being, if you take the force due to one charge and the force due to another charge and the force due to a third charge, so on and so forth, the total force acting on one particle is just the sum of those forces. That's the principle of superposition we talked about. Well, the electric field follows the same thing. So whenever you have any kind of electric field or electric charge distribution, you can then calculate the electric field acting on it. So let me give you an example. Let's say we have a charge Q, and let's say Q1 is actually equal to 3.33 microcoulombs. And we have another charge here, and that's, let's say, 4.44 microcoulombs. So that's 4.44. And let's make this one over here actually a negative. I'll make this one a negative. And what I want to calculate, or what I want to know, is what's the electric field right there at that point. Well, I'm going to tell you this distance right here is in fact 0.30 meters. And then this distance right here is in fact 0.40 meters. Okay, so we can calculate the electric field at that point. So first off, what I wish to know is the electric field at point P, which I'll label like this. So E sub P is equal to the electric field at P due to 1 plus the electric field at P due to 2, because this is charge Q2. So that's our principal superposition. It just says the electric field here is equal to the sum of the electric fields due to this guy and this guy. And if I had 40,000 of them, then I'd have 40,000 terms. But luckily I only have 2. Now, we're going to do the same thing we did before with regards to our magnitudes and direction, or excuse me, with regards to our directions. We're going to first decide the direction and then just do the calculation of the magnitude and make use of those directions. So first off, when I talk about E at P due to 1, then that's the electric field at this point due to that charge. Well, this charge over here is negative. So if I put a positive charge here, remember that you always test the electric field with a positive charge. So if I put a positive charge here, forget about this guy for a second, that negative charge, or excuse me, that positive charge is going to want to run towards that negative charge. So the electric field in this case is actually pointing to the left, which is a negative X direction. So this is E at P1 pointing to the left. However, when I have a positive charge here, that, and forgetting this guy and just thinking about that one, well, this is a positive charge. So lo and behold, a positive charge here also wants to run away. So I get, in fact, another electric field pointing this way, and that's E at P due to 2. So in fact, these two electric fields point in the same direction and along the same axis. So in this case, I'm just mathematically adding them, or arithmetically adding them. I don't have to add any vectors. I don't have to make any things about vectors. I just have to calculate their magnitudes. Does that make sense to everyone? Just by evaluating the magnitudes and seeing that they're parallel, that's just the same as regular addition. So what are those? Well, E at P due to 1 is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. Now, charge 1 is basically, if you notice, that's 0.3333 times 10, right? And 0.333 is 3 times 0.111. So it's actually 3/9 times 10. So I'm going to call this 3/9 times 10, not to the 6th, but times 10 to the negative 5th, because 3.33 is 10 times 3/9. Okay, so that's coulombs. Notice I didn't use the sign either. We're not going to use the sign with this no more than we did the other one. And the distance there is 0.30 meters, and that's going to be squared. So we can see that the 9 is going to cancel out with the 9. I'm still left with a 3 though, and the 10 to the 9th and the 10 to the negative 5th are going to cancel out, giving 10 to the 4th. So I'm basically going to have 3 times 10 to the 4th newtons times meters squared per Coulomb, and then 3/10 squared becomes 9/100. So it's 3 divided by 9 ultimately, which is 1/3. So I'll say 0.333. 100 will go up on the top, and that'll be 10 to the 6th. So 0.333 times 10 to the 6th newtons per Coulomb, because this was a meter squared down here. So that's the magnitude of that. I can call it 3.33 times 10 to the 5th if I want, because I divide by, excuse me, I'd multiply by 10, and then I divide this by 10, so it'd be 3.33 times 10 to the 5th. Again, this is all just me trying to avoid using a calculator. You just throw it in your calculator. Don't worry about this stuff if this doesn't come easy for you. I'm just trying to avoid using my calculator because I always make some kind of fat-fingered mistake. So the electric field at P due to 2 is actually 4.44. I think you can see what's going to happen is 444 is 4/9 times 10 again. So I'm going to say 9. I'll leave off the units this time. 9 times 10 to the 9th times 4/9 times 10 to the 5th again, because it's 10 times 4/9, and it was 10 to the negative 6. So now it becomes 10 times that, which would be 10 to the negative 5th. And all that will be over 4 squared is 16, so this will be 16/100. Okay. So that 9 is going to cancel out with that 9, and I end up getting 4 over 16, which would be 1/4. So I'd say 0.25 times 10 to the 100 times 10 to the 4th. That would be 10 to the 6th. So this is 0.25 times 10 to the 6 newtons per Coulomb. which I should write as 2.5 times 10. I'm going to multiply this by 10, but to keep it the same value, I got to divide this by 10, so I'm going to call this 10 to the 5th as well, newtons per coulomb. So adding these two, I think you can see I would get 5.83 times 10 to the 5th newtons per coulomb to the right is the actual electric field. So that's E at P. Okay, so notice all I did was calculate the magnitudes. It's not too big of a deal. Probably the most complicated part was me trying to avoid using the calculator, and that's fine. If you don't get it, that's okay. Just throw it in your calculator and be done with it. You should verify all these calculations, by the way, so you should like throw this in your calculator and see that you'll probably get something really close to 0.333. It might be well, yeah, you'll see that it comes pretty close. If you subtract the two, you'll see that it's basically off by 1 or 2 in this last decimal point. The same thing with this would be 0.25. But because these two electric fields both pointed to the left, the electric field due to this one, it's a positive charge. So a positive charge over here would want to go this way. So it points to the left. This is a negative charge over here. So a positive charge here would want to go towards it. So it points to the left as well. Therefore, we're just adding those numbers. Those numbers were 3.33 times 10 to the 5th and 2.5 times 10 to the 5th. The 2 plus 3 gives us a 5. The 5 plus 3 gives us 8. So that's 5.83. Does that make sense to everyone?
So why don't we use a negative 3.33 in the formula?
So the negative just tells us as far as whether it's going to be repulsive or attractive. The formulas that we're supposed to use, I just blindly teach my students to blindly cut off all the negative signs. Okay, just keep everything as positive, and then the Coulomb's law will give you the magnitude, and that's really what you want, because you don't want to use the signs to get the direction. If you did that, it becomes quite complicated. So it's best to just always calculate the magnitude as if all the signs are positive, and then use your reasoning about how positive and how like and unlike charges repel and attract each other.
Okay.
Okay. But that's a good question. That's the one that gets everybody. You know, you finish one semester of physics and you realize, okay, when I have a formula and I have a negative number, I got to put that negative number in that spot because it came out negative. And you're right, you know, when you're dealing with kinematics and stuff like that. But in electricity and magnetism, it's a little more complicated to do it that way. It can be done. In fact, when I teach the calculus space, we actually do include the sign, but it's a nightmare, and you can see why they reserved that for the actual calculus space course. So we've been going at it for almost an hour now, basically 45 minutes. I think this might be a good time to give you guys a little bit of a break and let you think about that example. So let's take a 10-minute break. Let's let you guys come back at 10:25, please. Again, I'm going to probably turn the camera off, but pausing. So anyways, that will be in the notes over here, but I'm also going to post it in an email. I'll send it to everyone so you can all meet on there. Thank you for making that. Is that OG that made it?
Okay, yeah.
Okay, thank you. Appreciate that. So we're now back recording. I've got the camera off because I'm a goober, and that's, you know, how I roll. Start video. Why is this error? Okay, so back to the picture of your handsome physics instructor. Okay, that's my story. I'm sticking to it.
I have
Anyway,
a question
yes,
on
ma'am.
the last question we just did.
Uh-huh.
Why did it go to the right at the end? Like, I'm just confused on why the direction was to the right in our final answer.
Oh, it wasn't supposed to be. Thank you for mentioning that. I remember drawing it to the left and I wrote the word right. That was, yeah, that's that goober in me. I keep hitting that button. Such a crackhead. So, yes. I said right. I drew left. Left was actually the correct answer. So it should be left, everyone. I apologize for that. Well, what a, I
Thank
did
you.
everything right, and I just said it wrong. Yeah, yeah. Feel free to catch me on that, and trust me, guys. If you think I did something wrong, you're quite certainly almost always right. And even if you're not, that's still a learning experience for everybody. So please, speak up as soon as you think I screwed up something, or I'll often just leave off a number. I was making one of the problems this morning that I posted on my YouTube page, on my YouTube channel, and forgot to divide by 3. And I was already at the end of the calculation when I had done it. And I was like, crap, just ruined everything. So if you guys catch that in real time, that's more helpful to everybody. So I appreciate that. Does anybody have any questions about what we did other than correcting me on that screw up?
Before we move on, I actually had a question about the inputs. I'm a bit confused on how we get Q and R.
How to get Q and R? Okay, so basically, whenever someone asks you, the book or me or whatever, asks you for an electric field, we've got to tell you the charge that's causing the electric field, and we've got to tell you how far away from that charge we want to know the electric field. So the charge that's causing it is the Q, and the distance away from that charge is the R. So it's sort of built into the question. If you refer to your textbook and look at some of the examples, you'll see, here's the wording of one of them, for instance. E at a point between 2 charges. This is almost identical to the problem I just worked. Actually, it's even the right, yeah, it's almost exactly identical. It says 2-point charges are separated by a distance of 10 centimeters. One has a charge of negative 25 microcoulombs and the other a positive charge of 50 microcoulombs. A, determine the direction and magnitude of the electric field at a point P between the 2 charges that is 2 centimeters from the negative charge. So they're asking for the electric field 2 centimeters away from the negative charge. So you've got your R there, and you've got your Q as the negative 25 microcoulombs, but in your formula, you're just going to use positive 25 times 10 to the negative 6. Does that make sense?
Yes, it does.
And then, of course, they didn't tell you what the distance is between the other charge and P, but you know the total distance is 10 centimeters, so 2 centimeters has been taken away. The other one's got to be 8 centimeters. So they can hide the number a little bit like that, but they've got to give you some way to get it, or you just can't solve the problem. All right. So now let's look for, we're going to do something that's basically what's called a dipole. So there's this thing in physics that we use a lot. It's called a dipole. There's dipoles, quadrupoles, octopoles, basically 2 to any power pole. So 2 to the first is a dipole, 2 to the second, oh, great, our internet's slowing down. 2 to the second is a quadrupole, 2 to the third is the octopole, so on and so forth. It turns out that is a helpful construct. I can give you a neat little story. A friend of mine said he was working at Los Alamos. No, it wasn't Los Alamos. He was working at Oak Ridge. That's what it was. He was working at Oak Ridge. And as an intern at Oak Ridge, they were studying gravity, and they needed a spherically symmetric object. And I don't know if you've ever worked in a machine shop, and probably most of you have not, but one of the hardest things you can ask a machinist to do is make a sphere. A sphere is a hard thing to do. You can certainly make cylinders all day long. That's a breeze, but a sphere is kind of hard. Well, they discovered that they couldn't make a sphere as exact as they wanted to, but if you take the equation for a sphere and you spread it out into a Taylor series, essentially, then you can see that a sphere can be made up of a dipole plus a quadrupole plus an octopole and all that stuff. And those things are actually pretty easy to make for an actual machinist. So they ended up combining dipole, octopole, and so on and so forth to represent a sphere that, even though it didn't look like a sphere, mathematically it was way closer to a sphere than what the machinist could make. So they ended up making this weird looking thing that was more like a Riemann sum of odd shapes. So it is a fairly important thing that's used in physics. The good news is, for the algebra-based physics people, they're usually not physicists, and they're usually not they're usually not astrophysicists either. So it's not something you're going to have to deal with too much, but you are going to hear the word dipole on occasion. And all a dipole is is a positive and negative charge of equal magnitude, but separated by some small distance. So you could have a plus 1 Coulomb and a minus 1 Coulomb. That would be certainly a reasonable dipole. If you have them 1 meter apart, then you need to know everything you need to know about them, because at the end of the day, there's something called the dipole moment. That is just the charge times the distance between them. So what we're going to do now is solve a electric field problem for a dipole. So I'm going to share my document cam with you. And I'm going to draw a y-axis right here. So this is my y-axis. I'm going to draw an x-axis right here. Again, I'm just drawing it. I normally don't even take the time to draw it when I'm solving physical problems, but in this case, I want you guys to be very certain what direction I'm calling positive x and what direction I'm calling positive y. So I'm making sure you have a good explanation of that. I'm going to put one charge right here at the origin. That's going to be Q1 is equal to, and let me be a pain in the butt again, I'm going to say 4.44 microcoulombs, and that one's going to be our positive charge. And then I'll say there's another charge over here, and that's Q2 is equal to negative 4.44 microcoulombs. And the reason I'm doing that, remember 4.44 is basically 4 times 1.11, and 1.11 is 10/9. So it allows me to get rid of that stupid K again. And what I want to do is I would like to calculate the electric field. Let's say this distance right here is 40 centimeters. And let's say this distance right here is 30 centimeters. And I want to know the electric field at that point P right there. Okay. So we really do have a triangle that's kind of helpful here. That's our 3, 4, 5 triangle again. And if you remember, the 3, 4, 5 triangle has very specific angles. For instance, if you take the inverse tangent of 3/4, you can find, oh crap. You take the inverse tangent of 3/4. I want to make sure I get the right number of decimal places and all that good stuff. So inverse tangent 0.75, and we get 36.9 degrees. So this is 36.9. I always forget whether this is the 1 and that one over there is the 9 or whatever. So that's why I wanted to verify it. And this, of course, if you subtract that from 90, you get 53.1 degrees. So that might come in handy. That's the reason why I chose 40 centimeters and 30 centimeters. And I already told you the reason I chose the 4.44. So we wish to know the electric field at point P. So that's easy enough. We're just going to use our superposition principle again. We're going to realize that there's going to be an electric field due to this charge at that point there, and there's going to be electric field due to this charge right there as well. We'll add those two up, and that'll give us a total electric field. So in symbols, that means E at P is equal to E at P due to 1 plus E at P due to 2. Okay? And then we just use Coulomb's law in the electric field version to calculate P1 and P2. So let's first get the magnitudes. Yes.
Sorry, how'd you get 36.9 degrees? I know you said inverse tan, but of what?
Of tangents opposite over adjacent. So it'd be 30 over 40.
Okay, thank you.
No problem. I was just pointing to the screen like y'all could see what I was doing. I just realized I'm an idiot. I literally was pointing to the screen. Oh gosh, I'm such a crackhead. Anyways, yeah. this is the angle here, so that's the opposite side. The adjacent always is the one that's touching it. So 30 over 40 gives me the tangent of 36.9. So when you take the inverse tangent of 30 over 40, which is 3/4 or 0.75, you get 36.9. All right, so let's calculate the magnitudes, and then I'll talk about the actual directions. So first off, EP1. EP1 is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. The charge of 1 is 4.44 times 10 to the -6 coulombs, which I think you recall is the same thing as 4/9 times 10 to the -6 coulombs. And then, of course, the distance between Q1 and P is 3/10 of a meter. So it'd be, all this would be over 3/10 meters squared. So obviously this 9 is going to cancel out with this 9. I'm left with 4 times 10 to the 5th, 10 to the -5th up top. And then this becomes 9 down here and over 100. So it's going to be 100 times 10 to the -5th, which would be 10 to the, 10 to the -5th times 10 to the 9th would be 10 to the 4th. 10 to the 4th times 100 would be 10 to the 6th. So it'd be 4/9, because the 4 came from there and the 9 came from here, times 10 to the, as I said, that would be 10 to the 4th times 100 would be 10 to the 6th newtons per Coulomb. And 4/9, of course, is, or excuse me, yeah, 4/9 is, of course, 4.44. Actually 0.44 times 10 to the 6 newtons per Coulomb. Or putting it in proper scientific notation, it'd be 4.44 times 10 to the 5th newtons per Coulomb, because again, I'm going to divide by 4, or excuse me, multiply by 4 here, but I divide by 4 there. Of course, I could have also realized that this 3 was going to become 9, and that would have canceled that out, and I just kept the 4/9, and everything would have been a lot simpler that way. So that's the electric field at P due to 1. The electric field at P due to 2 is the same thing. I'm going to leave the units off this time, times 10 to the 9th. Again, I'm not taking the signs. Remember, we never want to use the signs when we're dealing with Coulomb's law. We use the concepts to get our direction. And we're going to say 4/9 times 10 to the -6 over, now in this case, because it's a 3, 4, 5 triangle, that means this is 50 centimeters. Okay, so now that's a way that I found the R. Someone earlier asked about how do you find the Q and the R. The Q's were given here, but the R took a little bit of work. I actually had to use the Pythagorean theorem. R, because I knew the triangle, I did the equivalent of using the Pythagorean theorem. So I'm going to write this as 5 over 10 squared. So ultimately, this 9 will cancel out with this 9, and I'll get 4 times 10 to the 4th. Again, that's 10 to the -5th times 9, that'd be 10 to the 4th. And this would be over 25 100ths. So 4 over 25 times 10 to the 6 newtons per Coulomb. And you probably know 4 over 25 is the same thing as basically 16%. So that'd be 0.16 times 10 to the 6 newtons per Coulomb, or 1.6 times 10 to the 10 to the 5th, newtons per Coulomb. So I now have the two magnitudes, 1.6 times 10 to the 5th and 4.44 times 10 to the 5th. But in this case, they're not parallel, so it's a little more complicated. So first off, I'm going to draw EP1. So that's the electric field at P due to charge 1. Now this is a positive charge, And if I use a positive test charge, which I'm supposed to do, then I would know that ignoring this guy over here, the electric field right here due to this one is going to be straight up. And that's in my positive y direction. So I'm going to say right here is EP1. So EP1 points up along the y-axis. Now, when I deal with this guy, I see it's going to be along the line connecting the point and the charge. That's like Coulomb's law. Remember, Coulomb's law says the force is along the line connecting the two charges. Here we don't have two charges. We have a charge and the point. So it's going to be along this line. Now it's just a matter of determining which direction. Well, this is a negative charge, so a positive charge actually wants to go this way, and that's not along either axis. So I'm just going to draw this one as, let's draw it blue. So this is EP2. Okay. Now I need to actually treat this as a vector. I need to get these as vector components so that I can actually add them. So this EP2 has a positive x component, but it has a negative y component. So what I'll do is I will draw it like this. This is EP2y. And this is EP2x. Pointing that way. Now it's just a matter of using our trigonometry to figure out what is what. So again, don't be shy about writing all the trig functions. That's way better than making a mistake. So I will do it as if that's what's going on here. So for instance, if I take the cosine of 53.1 degrees, cosine is, remember, some old horse came a hopping. So cosine is adjacent over hypotenuse. So that'd be EP2y over EP2. And similarly, sine of 53.1 degrees is equal to opposite over hypotenuse, some old horse. So that's EP2x over EP2. So this tells us that EP2y is equal to EP2, which we found is 1.6 times 10 to the 5th newtons per Coulomb, times cosine 53.1 degrees. And we found EP2x is 1.6 times 10 to the 5th newtons per Coulomb sine 53.1. Now, using our special triangle, or 3-4-5 triangle, you can already tell that the sine of 53.1 is basically 4 over 5, or 0.8, and the cosine is 3 over 5, which would be 0.6. So you, in principle, could go ahead and do that without even doing using a calculator, but I'm not going to ask you guys to do that. I'm just going to go ahead and compute it now myself. 0.6 times 1.6, I know that should come out to be around a 0.7, excuse me, a 0.9 something. But 1.6 exponent 5 times, now I'll do cosine of 53.1 is 0.96 times 10 to the 5th, like I thought, which is roughly 0.9. So I'm going to call this 9.61, that's an extra decimal place, times 10 to the 4th newtons per Coulomb. This one should be roughly 0.8, and that should be 1.2 roughly. So I should expect 1.2 times 10 to the 5th or something. So 1.6 e to the 5th times sine of 53.1 is 1.28 times 10 to the 5th. Again, I'm carrying an extra sig fig there. So I now have the y components and the x components. So remember, the EP sub x is equal to EP 1x plus EP2x. Well, EP1 has no x component because it's purely along the y-axis, so that's just plain 0 plus. In this case, notice the EPX was actually a negative, so it'll be negative 1.28. And this is a really careful thing you got to be here. If you just blindly took that number without looking back at your diagram, you wouldn't remember to call this negative and you'd get the wrong answer. So always, 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 before you go to do the arithmetic, double check what direction everything's pointing so you can use the right sign. That's the whole reason I took the time to draw EPX. That was actually positive, sorry. Since I was doing X, that's actually the positive direction. And make sure I wrote the right one. Did I choose the right one? Yeah, I did write the right one. I just thought I was doing the Y first. That's why I chose a negative. So it is actually a positive, my fault on that. So that's the whole reason for me drawing this red one here, knowing that that's negative, and this green one here, knowing that that's positive. So when I'm doing the X components, I knew the EPX is in the positive direction, so I used a positive number instead of a negative, even though whatever, that error I just made. But all right, so I've got that. Now the EPY is equal to EP1y plus EP2y. Well, EP1 is all y. So I'm just going to blindly take EP1, which points in the positive direction. So that's 4.44 times 10 to the 5th newtons per Coulomb. And I'm going to add to it the EP2y. Now that's the one that is supposed to be negative. And that is, actually, I'll write it as 0.961 times 10 to the 5th. So they actually have the same, so I can sort of think about adding them in my head. But it will have to be negative. That's the key point, newtons per Coulomb. So basically, I'm subtracting about 1 from 4.44, only all of that's times 10 to the 5th. So I should get, remember this is extra sig fig, as is that one for that matter. So 0.96 from 4.44 should be 3.44 plus 0.04. So 3.48 times 10 to the 5th newtons per Coulomb in the positive direction. Again, that's an extra sig fig though. So hopefully I did that math right. I'm going to check it now with my calculator just to make sure I didn't do a bonehead thing like I often do. Yep, that's right. Times 10 to the 5th. Yep. So those are my two components. Now, how do I do this? Because I'm actually asking for the electric field. The electric field's a vector. So all I have now is the components. If we used IJK notation, which we learned in the calculus-based physics, we'd be done. We could just write 1.28 times 10 to the 5th newtons per Coulomb I hat plus 3.48 times 10 to the 5th newtons per Coulomb K hat, but we don't do that here. So what do? We have to reconstruct the vector from its components, and we have to take into account what quadrant it's in. Both of these components turned out to be positive, so that makes it a little easier. That means it'll be in the first quadrant. So I'll draw my X and Y axis again. There's X, there's Y. This is 1.28 times 10 to the 5th, and that's the X direction, and this is 3.48 times 10 to the 5th. So obviously this one's 2 or 3 times bigger than that one. So the Y is the bigger one. So what I'm going to do is I'm going to say the X is right about here, and the Y is way up here, say. So this is 1.28 times 10 to the 5th. and this is 3.48 times 10 to the 5th. So the ultimate vector is that guy right there, which we can get its magnitude. We can get its magnitude from the Pythagorean theorem. So EP magnitude would be square root 1.28, keeping that extra sig figs, times 10 to the 5th newtons per Coulomb squared, plus 3.48 times 10 to the 5th newtons per Coulomb squared, take the square root, and this is where I'll go ahead and round it to 2 sig figs because that's all I was given. So what I'm going to do is 1.28 e to the 5th squared plus 3.48 e to the 5th squared equals, take the square root of all that, and I get 3.68 times 10 to the 5th, which I'm going to call 3.7, where I've now made the proper number of significant figures, times 10 to the 5th newtons per Coulomb. That's the magnitude. The theta, the angle, is the inverse tangent of opposite, which would be this guy, which would be that guy. Both of them have 10 to the 5th, so I can just ignore that, and I'll just write it like this, over the adjacent, which is 3.48. So now I got to do is my inverse tan, and I'm going to say 1.28 divided by 3.48. You can go ahead and put in 10 to the 5th in both cases if you want, but I think you'll all see that they're just going to cancel out. And for that, I get 20.19 degrees, which I'm just going to call 20 degrees. So EP is equal to 3.7 times 10 to the 5th newtons per Coulomb at 20 degrees. If you ever give a angle that's measured counterclockwise from the positive x-axis, you can just say at that angle. You don't have to tell me anything else. If you use like this angle or some angle with respect to the y-axis or these negative x-axis or something like that, you have to include a diagram or do some wording to make sure I know what you're talking about. In this case, I had a diagram, so it didn't matter. But like I said, if you just put at that, I'm automatically going to assume that means you've measured it counterclockwise as measured from the positive x-axis. So that's how you turn that stuff in if you actually have to turn in something written to me. Far as someone asked me, are we looking for the cosine and sine to determine the direction it's going? The sine and cosine helps you find the components, at least when we were doing that up here, because we had, this is the vector we knew. This is what Coulomb's law gave us, was this magnitude right here, which turned out to be the 1.6 times 10 to the 5th newtons per Coulomb. But that wasn't along the x-axis or the y-axis, so I had to find a y component and the x component. So that makes a nice little triangle. It's a right triangle because x and y are perpendicular to each other. So then I can just use trigonometry and realize that the sine of 53.1 is opposite, which is EP2x, over hypotenuse, which is EP2, the 1.6 number. And the cosine similarly gives you EP2 EP2y over EP2. Any other question? Thanks for that, Riley. So yeah, ask me questions. You might not have your speakers. That's cool. When I'm working a problem, I usually don't look until the very end or at the very beginning, maybe in the middle part. So also, if a student does have a speaker and they see a chat question come up while I'm working the problem, feel free to say, Mr. Younger, there's a chat question, and I'll answer it in real time. So I'll be more specific about exactly what problem or what part of the problem you were asking about. Any questions on that? So that's a typical type of problem you would have to be required to solve in this course. It's a typical test type problem sort of thing. Another one that we do with the dipole is we normally calculate what the electric field is directly over the center. So I'll go ahead and do that now as well. So let's work that problem. Let's say what is the electric write it so y'all can see what is the electric field at 30 centimeters above the center of this dipole. So let's take that same dipole and let's calculate what the electric field would be dead center above it. So in this case, I'll sort of move along my x-axis a little bit. Well, actually, I can just leave it there. So this is the positive 4.44 microcoulombs, and this is the negative 4.44. This is the negative 4.44 microcoulombs here. And if I go over 20 centimeters, I'd be right about, well, actually I'd be more like there. And if I go 20 centimeters from this way, I'd be at the same spot. So that's dead center right there. Notice they were 40 centimeters apart. So now I'm going to go up 30 centimeters, and that's the point P. Okay? So we want to know the electric field right there. Now the key with this is you realize that the electric field due to this one is going to be along this line, and the electric field due to this one will be along this line. And just from the symmetry, this is 30 and this is 20 and this is 30 and this is 20. This angle has to be the same as this angle. And in fact, what you get is an electric field that points this way, because notice a positive charge, if I put it right here, wants to get away from this positive charge, so it's going to go that way. This one, on the other hand, a positive charge wants to come towards this one. So it should be like there. And notice these are about the same length, because symmetry tells us that since they're the same order of magnitude and the same distance away, here and here are equal, then these should have the same magnitude. But what you get is, completing the parallelogram, and then parallel to this, we see that the net result should be just an electric field pointing that way. So really all that matters is the x component of this electric field and the x component of this electric field, because those two are going to add up. The y components, in fact, are going to disappear. As you can see, the y component for this one's going to be negative. The y component for this one's going to be positive. But the x component in both cases are going to be positive. Okay? So by all the symmetry, this problem actually turns out to be a lot easier, because all I have to do is calculate the electric field due to either one, since the distance is the same for both of them. The charge is the same for both of them. Then because of that, I automatically will have the same magnitude for both of them. So EP1 equals EP2 equals 9 times 10 to the 9th. Let's leaving off the units just to be quick and loose. Times 4/9 times 10 times 10 to the negative 6th. All that divided by, now this time the distance is not 20 and it's not 30. It's going to be the square root of 0.20 squared plus 0.30 squared. And then, of course, that gives us the r, but I need the r squared, so I'm going to have to square that. So obviously this 9 is going to cancel out with that, and I'm going to get 4.44 times 10 to the -6, it'd be -5, and 9 would be 4. All that newtons per Coulomb divided by whatever this square number is down here. So I'm going to do 0.2 squared plus 0.3 squared. And that is actually r squared. I take the square root to get r, and then I square it to get r squared. So I'm going to divide this by 0.13. That's actually what it ends up becoming. So that's basically 13 over 10 if you wanted. But either way, I'm going to do 4.44 times 10 to the 4th divided by 0.13. And I get 3.41, 42, excuse me, times 10 to the 5th newtons per Coulomb. So that's the magnitude of this guy. That's also the magnitude of this guy. If I want the x component, I know this angle is the same as this angle, so it's the inverse tangent of 30 over 20. So all I really need is to find out what that angle is. Theta is equal to tangent inverse of 30 over 20. And so 3 divided by 2, that's 56.3 degrees. So I now know that angle right there, which is the same as that angle right there. So one x component is going to be would be 3.42 extra sig fig times 10 to the 5th newtons per Coulomb times the cosine of 56.3 degrees. I get, oh, excuse me, I get 3.42 e to the 5th times 56.3 cosine. You get 1.89, actually 1.90 times 10 to the 5th newtons per Coulomb. That's just one of them. The other one's going to be identical. So the actual electric field would be twice this big, which would be 3.80, which I'm going to round to 3.8. So ultimately, EP is going to be equal to 3.8 times 10 to the 5th newtons per Coulomb. And this one does actually point to the right. In other words, you could say it 0 degrees, or you could just say it points to the right. That's all acceptable. So hopefully that helps you. So you see how we did that one? That one was a little, well, I made it easier. That's why I tried to fit it into the that small bit of the bottom of the page. So what happened was we have an electric field due to this one that points along this line, and since it's a positive charge, it points away from it. We had an electric field due to this one that points along this line, but since it's negative, it points this way. Those two are equal in magnitude because the only thing they depend on is k, which is 9 times 10 to the 9th for both of them. This distance, which is the square root of 0.2 squared plus 0.3 squared, and that happens to be the same as this one. And they both have the same magnitude of the charge. So the magnitudes are automatically equal. These two have to be identical in magnitude. Now the direction is quite different, but their direction is similar in one way. They both have the same x component, and they both have the same magnitudes for the y component, but the y component for this one is positive and the y component for this one's negative. Since they're equal in magnitude, that means they're going to cancel out. So all I'm really going to do is, or all I really had to do was add the two x components or multiply the x component by 2, and that would give me the actual total vector, or the total electric field magnitude. And what I calculated was the x component was 1.90 carrying that extra sig fig times 10 to the 5th. When I multiplied that by 2, I got 3.8 times 10 to the 5th, got rid of the extra sig fig, and just kept it as 3.8 times 10 to the 5th newtons per coulomb, pointing to the right. So you could say at 0 degrees if you wanted to, because then that's the same thing as measuring counterclockwise from the positive x-axis, only you measure an angle of 0 degrees. Anybody have any questions on that one? Okay. Well, the rest of the stuff we got to do is finishing off a little bit about conductors, electric fields and conductors, which you can read, of course, in your textbook, and you need to read it. You need to read the whole chapter, of course, so you can do the homeworks. But I'm going to give you a rough synopsis of that, and then I'm going to go into chapter 17, which is somewhat mostly conceptual, but there's going to be a little part where I'm going to do some math and maybe not even work any mathematical examples, but I might post some later on my YouTube channel. So let me stop with the document cam and turn back to me. I could give you a break, but I think I can just finish. Does anybody need a break? Okay. All right, so I'm just going to go with this. So one thing you need to know is a conductor is an object that is a material that the atoms or the molecules that make up the conductor do not hold on very tight to at least their outermost electron. Sometimes it's more of them that it doesn't hold on to very strongly. So basically, when you get all these conductor molecules or atoms together and make a big blob of conductor, then the electrons are sort of free to move all around inside the blob, right? That's what a conductor is. If you had an electric field inside of that conductor, then the individual free electrons would be running in the direction or the opposite direction of the electric field, because remember, the electric field is the direction a positive charge would go, and free electrons, of course, are negative, so they go the opposite direction. When that happens, then you have something called a current. When electrons are moving uniformly in a single direction, then that is a current, and that's what we call a non-electrostatic situation. Okay, in electrostatics, we don't expect the actual charges within the conductor to move. So in a static situation, what we can conclude is that no electrons should be making a net movement. In other words, just as many will be moving to the left as they're moving to the right, just as many will be moving forward as they're moving backwards, and just as many will be moving up as they're moving down. Okay, on average, that's the case. When that's the case, you're actually dealing with a static situation. There's no current, and therefore the electric field in a conductor is 0. Now, another thing is when you have charges on an electric field, they all distribute themselves along the outsides of that conductor. So when you have charges, I think I said an electric field, when you have charges on a conductor, they will all try to get as far away from each other as possible, and the best chance they have at doing that is distributing themselves on the outside surface of that conductor, and in so doing they distribute themselves uniformly over it so that at everywhere the electric field points perpendicular to the surface. So if, for instance, well, I can't do that because I was full of coffee. If, for instance, this shape right here is a conductor, then equal number of charges per each centimeter will line up along here, and because of that, all the electric field will be perpendicular here, perpendicular here, perpendicular here, perpendicular here, and over here it'll be perpendicular like that, and over here it'll be perpendicular like that. So the surface of a conductor always has the electric field lines leaving it perpendicularly. That's going to come in handy in our lab today. Okay, so those are big things. Another thing is inside of a conductor, you should have 0 electric field unless there's a charge in there with it. So for instance, if you had, let's say, a wedding band conductor like this, okay, so you have this ring, And if there's electric field out here, basically it's going to stop right there in 2 dimensions. Now, in 3 dimensions, it'd have to be a sphere. But if you had a spherical metal and you immersed it in an electric field, the inside in here would have 0 electric field. That's actually called a Faraday cage. And in fact, Ben Franklin was one of the first people to come up with one. And some poor sap over in, I say poor sap, some poor guy over in France built one on top of a steeple of a church and didn't quite do it right. So he got struck by lightning and burnt. It was not a good experience at all. But in general, a Faraday cage is super, super safe. Do a search if you'd like sometime with Google. Do a Google search for Tesla coil, Tesla, like the scientist Tesla, coil, COIL. And you'll see this thing that creates huge, powerful lightning strikes. And you'll find some of them will have people interacting with them just by being in let's say a chicken wire coop or something. So you can make a little suit out of chicken wire, and that makes basically a Faraday cage, all because the electric fields will not penetrate the conductor. So if you, on the other hand, let's again take this ring, which we're pretending to be a sphere because it's 3 dimensions, but in 2 dimensions, it only need to be a circle. But if this was a sphere in 3 dimensions and it was immersed in electric field, like I said, all the electric field would die inside. But if you then put a charge in the middle, then it's going to have the electric field due to that charge inside of it. But then inside of the metal itself, inside of the metal, there's going to be 0 electric field. And then outside, you still have the electric field that was out there. So those are some of the concepts of electric fields and conductors. The next thing we're going to go into is chapter 17, where we're talking about basically voltage. So there's something that we call electric potential, and electric potential is basically the electric potential energy per unit charge. So if you take the potential energy, which we've learned about in last semester in the first part of this course, you'd learn that potential energy and energy in general is measured in Coulomb, or excuse me, is measured in joules. So, for instance, we had gravitational potential energy was mgh. At least when you're close to the surface of the Earth, it was just mgh. That would come out in joules because it turned out to be a m was a kilogram, a g was 9.8 meters per second, and a kilogram times a meter per second is just like ma. So that's a Newton. And then the h would give you a meter, so a Newton times a meter is a joule. So potential energy is a joule, kinetic energy is a joule, nuclear energy is a joule. Everything can be converted, every type of energy can be converted to a joule. Now, if you take the potential energy due to, let's say we put there's a positive row of charge right here, bunch of positive charges. Now I take this positive charge that's over here and I put it right up against it. It's not very comfortable, right? Because positive charges don't like being near positive charges. So it's got a lot of potential energy. I think of energy in general as the ability to do work. And if you remember, work is a force times a distance. So a way of thinking about the ability to do work is, can something drive a nail? What do I mean by that? Well, you can imagine as thin and slight a nail as possible. So it could be like a straight pin that's super, super sharp and has a very small diameter. And it could be going into something super, super soft like marshmallow. Okay. If you have the ability, if something has the ability to push that pin into that marshmallow, then that thing obviously had some energy because that energy was able to do work. So potential energy is the ability to derive some energy or to do some work. So this positive charge being next to this positive plane of charges here has the ability to do work, because you can imagine this positive charge being shot off, running into the head of a nail, pushing it into a marshmallow. Okay. And if in fact there was another plate over here that was negatively charged, okay, negatively charged here, positively charged here, if that was the case, as the positive charge got closer and closer to this one, it would feel more and more comfortable getting closer and closer to this one. So this one would actually cause it to speed up as well. So either being here this far away from the negative charge, the positive charge wants to be here, or being this close to the positive charge wants to be there. So in the end, you basically get a scenario where it's going from high potential energy to low potential energy. If you did that with a array of charges in what we call a capacitor, which is a plate of uniform charge, basically, very close to another plate of uniform opposite charge. So maybe this one has a total charge of 5 microcoulombs, and this one has a total charge of negative 5 microcoulombs. If you're really close to the center, not near this edge or this edge down here, then the electric field is quite uniform. It's a constant, in other words, and work is equal to force times distance. Well, the force is just QE. So watch this. I'm going to share my camera for a second, my document camera for a second. So if I had a positively charged plate here that's really big compared to how far apart it is from this negatively charged plate, I put the same number of charges on there so they look like they're uniformly charged. Well, what's happening here is I have a series of electric field lines that point this way, and they're completely uniform here in the middle. Once you get over towards the side, to the edge, though, they tend to bend out a little bit like that, and like that, and like that, so on and so forth. But at everywhere where they're touching the conductor, they're actually hitting the conductor perpendicular to the surface, as we talked about before. So by taking a positive charge from here to here, the work done is equal to force times distance when the force is uniform, and in this case it is. So the force is actually the charge Q times the electric field E. That was our definition of electric field. But then the distance is really the separation between the two plates, D. So that's the actual work done. And that actually, notice it went from a high potential energy to a low potential energy. So the change in potential energy, which is always potential energy final minus potential energy initial, that's what the delta always means, that has to be a low potential energy minus a high, so that has to be a negative value. In fact, it's the negative of the work done. That's what potential energy is. Potential energy is the negative of the work done in going from the initial point to the final point. So the change in potential energy would actually equal negative Q times E times D. Okay? Now, if you want the actual voltage, then the change in electric potential, notice I'm saying electric potential, not electric potential energy. This is electric potential energy. It has units of joules. Okay? The electric potential is another thing. That's what we call voltage. And the electric potential is the basically the change in potential energy divided by the charge. So it's the change in potential energy divided by the charge. So in this case, it would actually be a negative ED because the Q canceled out. In other words, it was QED over Q, negative of that, and that just became E times D. So I think you can now see why I told you that the electric field will have different units later. If you saw this for electric field, just in terms of units, the unit of the electric field in this case would be the unit of the change in voltage over the distance. So we see the unit for the electric field is also a volt per meter, not just a Newton per Coulomb. So the unit, by the way, as I mentioned it already, but the unit for the voltage or for the electric potential is volts. So those are the big, that's the big equations that we're dealing with right now. It gives you something that's sort of like the electric field. Remember, the electric field tells us how something's affected independent of what charge it is. Well, by taking the charge that was playing the role here out, by dividing it out, I now have something about the space itself. The good news is this voltage, though, is a scalar, so I never, ever, ever have to do vectors. Excuse me, never have to do vectors. It's a scalar number, so I just have to deal with the magnitudes. That is what the electric potential is. Electric potential, if you find all the points that have the same voltage, and then you connect them all with a line, that line or that surface, if you in 3 dimensions, is called an equipotential surface or an equipotential line. We're going to use that today in our lab. We're going to find all the places that have the same voltage between, you know, 2 charges, and then we'll connect them with a line, and those will be the equipotential lines. It turns out the equipotential lines are perpendicular to the electric field lines. And in fact, ultimately what we get is that the electric field, for those of you who have ever experienced calculus, is actually the x direction would be the negative derivative of the voltage with respect to the x. For those of you who have never seen or heard about calculus, the electric field in the x direction is about equal to the negative of the change in voltage divided by the change in x. So in other words, if you're looking at this electric field lines, or let's say the equipotential lines, let's say this is one equipotential line, this is one equipotential line, this is one equipotential line. Let's say this one has a voltage of 10 volts and this one has a voltage of 5 volts. And let's say the distance between them, delta x, is 1 centimeter. Then the electric field in here in the x direction is approximately equal to final minus initial. That would be 10 volts minus 5 volts over 0.01 meter. So that'd be 5 volts over 1/100th of a meter. So that's 500 volts per meter. So that's really, and actually a negative should be in there, but that's just dealing with a magnitude. That tells you if you have a 10 volt or 5 volt separation over 1 centimeter, then the electric field strength is in fact 500 volts per meter there. And what we're going to do in lab today is we're going to make a distribution of charges like this and this, and we'll find all the equipotential lines by finding all the points that have, say, a voltage of 1, all the points that have a voltage of 2, all the voltages that have a point, or all the lines are points that have a voltage of 3, and so on and so forth. Connecting all those like voltage planes creates an equipotential surface, and then we just remember the electric field has to be perpendicular to it. So we say, well, it has to be perpendicular to the conductor, it has to be perpendicular to the equipotential, and it has to be perpendicular to all the equipotentials. So lo and behold, we got a line that goes like this. And obviously this is the direction that a positive charge would go. It would go from 10 volts to 5 volts. So the electric field points this way in this case. That's why the negative came out, by the way, in there. Any questions on that? All right, so basically we went up through 17.3. The last thing I wanted to let you know is we now have this formula where we know that the potential energy is actually equal to, or the energy in general is actually equal to the charge times the voltage. So change in potential energy is equal to Q times change in voltage. Because of that, there's a really nice unit that we'll use occasionally rather than the joule for potential energy. We can, for instance, realize that if we put an electron whose charge is 1.602 times 10 to the negative 19th coulombs, if we allow an electron to go through a voltage of 1 volt, then that would actually give us an energy of 1.602 times 10 to the negative 19th joules, right? By that formula, 1.602 times 10 to the negative 19th times volts. A volt is defined to be a joule per coulomb. Okay, that's the actual unit. So when I multiply a joule per coulomb times a coulomb, I just get a joule. So 1.602 times 10 to the negative 19 times 1 gives me 1.602 times 10 to the negative 19 joules. Well, we define that energy to be 1 electron volt. Notice it looks like the formula. If I replace Q with an E and I replace delta V with a V, lo and behold, you get the unit. So that's called the electron volt, and it's 1.602 times 10 to the negative 19th joules. It's a small unit of energy, which makes it ideal to deal with electrons and protons and stuff like that. So that's the last part that we're doing today. I need to clear my throat a little bit. I'm going to give you guys a break until 12, and we'll come back and discuss lab at that time. So we'll go ahead and I'm going to pause this.